Hi there everyone, welcome back to the channel. I'm the GCSE science teacher, and in today's video we're going to be focusing on covalent bonding in terms of giant covalent structures. This is part of the chemistry topic we've been learning here so far. If you do want to see previous topics from me, check out my YouTube channel. I have put things into playlists now, so if you do want to see those, I will link that for you at the end of this video. Thank you also if you have subscribed. It is so good to have you as part of our community here on YouTube, just because there are some new people who have joined us. I am a real science teacher. I teach all the way from Key Stage 3 all the way up to Key Stage 5, and my specialism is biology, but I do teach chemistry and physics as well. So if you do want any specific content covered from me, perhaps you've got a mock exam coming up, I know a lot of my students currently do, I'm always happy to share any tips and tricks or any revision you want. Just let me know in the comments below, because it's always great to hear from you. So yeah, let's get on with it. Covalent bonds then, a bit of a recap. It's a shared pair of valent electrons. Essentially, that means electrons that are in the outer shell that are shared between atoms. Specifically, though, they are non-metal atoms. And if you don't know where in the you find out if something is a metal or a non-metal, you would go to the periodic table, and everything on the left-hand side is a metal, and everything on the right-hand side is a non-metal. And if you want to learn more about the periodic table, I'll link a video for you that I made a few weeks ago. Covalent bonds are incredibly strong, which is why all the structures that have covalent bonds in them have very high melting points. It takes a lot of energy to break those bonds apart. And we do actually find covalent bonds in loads of places within the world. So we have them, say, in glucose, which can be stored as starch in plants. We have cellulose, which is also another polymer of glucose that's found in cell walls. We have methane, which is a greenhouse gas and also a hydrocarbon. It's released from cows. We have water, we have carbon dioxide, carbon monoxide, a poisonous, dangerous gas, which is odorless and colorless, hard to detect. We have oxygen. So there's loads of different compounds and molecules that have covalent bonds, but today we're focusing specifically on the giant covalent structures and how the different structures kind of are similar but different. A lot of the questions to do with this are comparative questions, long answer questions, and also identifying the structures as well. So let's get into it. So if we look at the different types of giant covalent structures you need to know, some of them are categorized as allotropes of carbon. An allotrope of carbon essentially is a structure that is only made up of carbon atoms. So we have, for example, diamond, graphite, graphene, and fullerenes. All of these are made only of carbon. However, we also have another giant covalent structure called silicon dioxide, or silica, and we're going to talk more about that in a moment. But you can see just by the pictures I've placed here, all of these giant covalent structures actually have really high usability. So some of them are found in electronics, some of them are found in jewelry, in industry, the medical industry, things as simple as pencils. A lot of these giant covalent structures we've actually seen in everyday life, and we might not have even realized. So they're highly useful structures, and we're going to talk about each one individually now. So the first one we're going to talk about is diamond. Diamond is obviously found in jewelry. It can also be used in industry to actually cut other materials because it's very, very hard. And diamond's very hard because of the giant covalent structure that it has. It's a tetrahedral 3D structure. Essentially, that means the carbon atoms that are found within each form 4 bonds with other carbon atoms, and these bonds are covalent bonds, of course. Those bonds are arranged in specific angles that give it this tetrahedral shape. I'm not going to go too much into bond angles at this point because that's more of an A-level realm, if you will. But you need to know that it has a tetrahedral shape and that each atom of carbon forms 4 bonds which are with other carbon atoms. Now, because each carbon atom can make up to 4 bonds, that means all of the electrons are shared. There are no delocalized electrons here, which is why diamond does not conduct electricity, but it has a very, very high melting point because there are so many strong covalent bonds there. And that's one of the comparative points you need to be aware of. Remember, diamond is obviously made from carbon, and to get natural diamonds, you actually need to put it under high amounts of heat, around, I believe it's 160,000 degrees C or 1600 degrees C. It's very, very high. And for the pressure as well, it's like 50,000 times the pressure on Earth, the atmospheric pressure. So it takes a long time for diamonds to form. We can also get them artificially created as well, but diamonds in their natural raw state, they take a long time to create, and but they're also very difficult to destroy as well because they're so strong too. The next type of structure we need to be aware of is called graphite. Now, graphite is often found in pencils, and some people believe that pencils are made of lead. They used to be, but lead is obviously a poisonous metal. So, for health and safety reasons, we've changed it to graphite, which is a very soft, non-metal structure, and that's why we're able to write with it. And the reason it's soft, even though it's still made of carbon, and essentially you could say it's still made of the same stuff that diamond is, the reason it's soft is because of the way the atoms are arranged. So in the case of graphite, each of those carbons are covalently bonded to three other carbons. So there is only three bonds this time, and they're in this hexagonal ring shape that actually forms layers. Now those layers are able to move over one another, which is why it has a soft property. But also because there's only three covalent bonds per carbon atom, we actually have some delocalized electrons going on, and that means that graphite can actually conduct electricity, which is really useful, especially as we move on to the other types of covalent structures which also use graphite, and I'll talk about that in a moment. So the other thing to be aware of is because it's in layers, some students will make the mistake to say that there are covalent bonds between layers. There are not. There are only covalent bonds between the carbon atoms themselves. What happens between the layers is an intermolecular force, and that's slightly different and slightly weaker than the covalent bonds that you see between the carbon atoms. The next type of structure is called graphene, and graphene is very similar in terms of graphite because graphene is made of a single layer of graphite. And essentially, graphene is used to make things like electronics. It can also be used for composites, which is a type of material that's made up of a mixture of materials that have certain qualities. But the reason they're used for electronics is because graphene, because it's made of graphite, has those delocalized electrons again, and they can conduct electricity. Now, because it's a single layer, you don't have those intermolecular forces, but you do have very high melting points because of the covalent bonds between the atoms as well. So that's something that you can say as a comparative point. The next one is a fullerene, and there are two types of fullerenes that you need to be aware of. We have Buckminster fullerene or buckyballs, which is a very large structure. It's C60, so there's 60 carbon atoms all connected in a hexagonal ring, each forming a spherical shape that's hollow, kind of like a ball essentially with a hollow interior. We also have a nanotube, which is essentially a very thin tube that's made of those carbon atoms again. Now, the actual nanotube itself is essentially made of the graphene layer that's rolled into that tube. It has a very small diameter compared to the length of the actual nanotube, which means that it has a very high tensile strength. So it's very strong. It's not easily stretched. Both of these have uses in electronics, in nanotechnology, but also in other industrial uses as well, like medicine. One thing you need to be aware of in terms of the actual structure of both, like I say, they're both hollow. They can form hexagonal rings of carbon, but they can also have a pentagon shape. They can even have heptagon shapes as well, which have either 5 or 7 carbons respectively. Both of them do have those carbon covalent bonds, but one thing to be aware of is the Buckminster fullerene have weak intermolecular forces between the molecules, and that gives it a lower melting point. Remember, the covalent bonds are strong, but anytime you see intermolecular forces, that's talking about the molecules and the interaction between them, and that can actually be a lower melting point to break those molecules apart. And then the last one is not an allotrope of carbon. Don't get caught out with this one. This is silicon dioxide or silica. Essentially, this is made up of silicon and oxygen atoms, so nothing to do with carbon, but it is a giant covalent structure because it has so many covalent bonds. It's the main component that's actually found in sand and glass. It has a very regular arrangement. It's solid at room temperature. It has this sort of white powdery substance that you'd see to the naked eye. And because of those giant covalent structures, it has a very high melting point and a high boiling point. And that's something that you can use to compare with the other giant covalent structures that we've discussed today. And the last thing from me in this video is a bit of fun. It's the month of December. I'm doing a curiosity calendar, a bit of an advent calendar, a countdown to Christmas. If you want a bit of sciencey fun, over on my Instagram and TikTok, I'm posting every single day for the month of December a interesting did you know fact that links the GCSE curriculum to the winter period, the festivities. If that's something you're interested in, feel free to follow over there. Also use the hashtag ScienceMus, which I have created or utilized, I should say. I don't know if it's already out there, but if you do anything fun, maybe a practical, if you do any homework or anything exciting, use that hashtag, tag me. I'd be more than happy to see it. I'd like to maybe get a bit of a buzz going on around the internet about the amazing work that's going on in science in schools. So if you are interested, definitely do that and tag me, and I can share that on my Instagram, my TikTok, or even on my YouTube as well. It's always good to see what you guys are up to in terms of science related content. And then, yeah, that's the last bit from me. So I have been the GCSE science teacher and you have been curious. Thank you so much for your time today. If you did enjoy it, please feel free to like and comment down below any topics you want help with. Subscribe if you haven't already and be part of our community. And I will see you in the next one. Thanks so much. Take care. Bye.